Most people think platinum is the most expensive metal on Earth. It's totally not. 6 metal on this list beat it, including gold. We are going through the 20 metals today, from the cheapest to the most expensive. Some of them you know, some of them you touch without realizing this, some of them you used without realizing it either, and a few of them can barely exist long enough to matter. Let's start from the bottom. Rhenium. Rhenium is one of the rarest elements in the Earth crust. Gold is nearly 3 times more abundant. It wasn't identified until 1925, when Walter and Ada Noddack finally isolated it, long after most stable element were already known. It was the last natural occurring element to be discovered. Even today, it's not mined directly. It's show up in a tiny amounts and is pulled out as the byproduct when processing molybdenum and copper ores. That alone limits how much of it exists on the market, but where it show ups matter. Rhenium goes into superalloys used in a jet engine, especially turbine blades. Here's what it's actually mean. Those blades operate at the temperature that exceed the melting point of the alloy itself. The only reason they survive is their structure, engineered at the microscopic level to resist what should destroy them. Adds just 3 to 6% rhenium, and that structure holds under sustained heat and load. That one detail changed everything. Higher temperature mean higher efficiency mean better engines. So even though rhenium trades at only $7 per gram, it quietly defines how far modern aviation can go. So every time you fly, you're technically using it. Ruthenium. Ruthenium discovery almost didn't happen. In 1827, 2 chemists examined platinum ore from the Ural Mountains in Russia. One found nothing, the other thought he found 3 new elements and couldn't replicate any of them. It took until 1844 when Collar Ernst Claus finally isolated it properly. He kept the name Ruthenium, the Latin word for Russia, where the ore came from. It sits in the same family as platinum and palladium, but it doesn't show up in obvious places. You won't see it in a jewelry, you won't notice it directly. Instead, it sits inside of the systems. Ruthenium used in a thin film resistor, the component that controls electricity movement through circuits. Without that control, model electronic, the one that I'm using in those cameras, for example, don't behave consistently. It also does something striking with other metals. Add just 0.1% of ruthenium to titanium, and that titanium becomes 100 times more resistant to corrosions. It straightens palladium and platinum alloys the same way, harder, more stable, more resistant to wear. So ruthenium doesn't stand out on its own and stabilize everything around it. It trades roughly at $55 per gram, but its value isn't the price, it's control. Palladium. Palladium was discovered in 1803 by William Hype Wollaston, who named it after asteroid Pallas. Today it lives inside something most people use without thinking about, the catalytic converter. Every gasoline car has one. Inside it, palladium drives the chemical reaction that turns toxic exhaust into less harmful gases. A typical converter contains about 2 to 7 grams of palladium. The number sounds small until you scale it. Millions of cars, constant demand, no easy substitute. That's what pushed palladium into one of the most aggressive price movement in the recent history. Between 2019 and 2021, it reached roughly $90 to $100 per gram, briefly overtaking the gold. Today it sits roughly at around $60 per gram, but the mechanism hasn't changed. Industrial dependence defines the price, and when supplies can keep up, even a few grams become valuable enough to steal, which is exactly why catalytic converter theft become a real problem. In US, report theft went from roughly 3,500 in 2018 to over 14,000 in 2020. Right now it's probably even more. One metal drove almost all of it. And there is another entry on this list that makes this number look smaller. Platinum. Platinum was known in South America long before Europeans understood what it is. When it finally reached European scientists, it was dismissed as the inferior form of silver. The name actually reflects that, platina or little silver. That perception didn't last. Platinum is denser, stable, and resistant to corrosion in a ways few metals are. It doesn't react easily, it doesn't degrade under conditions that destroy others. It also sits in the same emission control system as palladium, doing similar work under the same constraints. But platinum goes further. In jewelry, it's used at around 95% purity. It's heavier than the gold, about a third heavier than the 80% gold at the same volume. Hold a gold ring in one hand and platinum in the other hand, and your brain notices it immediately. That's why many of our clients confused why platinum rings more expensive than the gold ones, simply because you need more metal for the same volume. And it feels permanent in a way gold doesn't quite match. In medical, platinum compounds like cisplatin are used in chemotherapy. The first FDA-approved platinum cancer drug in 1978. That alone places it in a category beyond decoration. And yet, despite everything it does, platinum trades at about $70 per gram, which I think is underrated. And also which leads to a simple contradiction. It sounds more premium than gold, but gold at around $150 per gram is currently more than twice as expensive. So the label doesn't match the market quite yet. Gold. Gold doesn't need introduction. It has been used as the money, as the decoration, as a symbol of wealth for thousands of years. Entire economies were built around it, entire system trusted it. That consistency comes from its properties. Gold doesn't rust, it doesn't corrode easily, it's soft enough to shape but stable enough to last, and it has a color that doesn't need explanation. Today gold trades at around $150 per gram, but it doesn't stop at culture. A typical smartphone contains about 200ths of a gram of a gold used in microconnection because it conducts electricity reliably and doesn't degrade. In space, gold appeared in a completely different form. For example, the visor of Neil Armstrong helmet during the first moon landing mission was coated with a layer of gold so thin, about 50 nanometers, that he could see through it. That layer reflects infrared radiation and protect his eyes from unfiltered solar exposure. The same principle is used on satellites today. So gold sits in two worlds at once. It represents value and it solves real engineering problem. Iridium. Iridium was discovered in 1803 by Smithson Tennant, the same chemist who found osmium that year, in the same residuum from the same dissolved platinum ore. Its name comes from the Greek word iris, meaning rainbow, referring to the range of colors seen in the compound. What defines iridium is resistant. It doesn't react easily with acids, it doesn't corrode, it does hold its structure under conditions that break most of the metals. That's why it shows up in the places where failure isn't an option. Modern spark plugs rely on iridium. The working tips is often less than 1 mm in size, but it has to survive constant electrical discharge at the high temperatures. Standard materials wear out, iridium doesn't, at least not nearly as fast. That small difference expands the lifespan of components significantly, but iridium also appears in a completely different context. In 1980, physicist Luis Alvarez, a Nobel Prize winner, and his geologist son Walter were studying a thin layer in a limestone near Gubbio, Italy. The layer sat right at the boundaries between the Cretaceous and Paleogene periods. They found iridium at concentration 30 to 160 times higher than normal. Then they found the same layer at the same level at hundreds of other sites around the globe. Iridium is rare in the Earth crust because it sinks the core during the planetary formation, but it's common in asteroids. The only explanation that fit was the impact. The Chicxulub crater, 200 kilometers across from Yucatan Peninsula, was eventually confirmed as the site. 66 million years ago, 75% of the species gone. That thin iridium layer what proves it. So the metal connects the components inside of the engine to a planetary scale event. It trades at around $280 per gram. Rhodium. Rhodium was discovered in 1803 by William Hyde Wollaston, shortly after Palladium. Its name comes from the Greek word rhodon, referring to the color of some of its components. It operates inside of the same system as Palladium, the catalytic converter, but handles a different part of the chemistry. Rhodium reduced nitrogen oxide, some of the most harmful gases in the vehicle emission. The amount is used extremely small. A typical catalytic converter contains only 0.1 to 0.3 grams of rhodium, less than the weight of the paperclip. But the value doesn't come from the volume itself, it comes from constraints. Rhodium is rarely mined directly. It's the byproduct of platinum extraction. That means supplies depend on something else. You can simply decide to produce more rhodium when demands increase, and when demands rises, prices react. Around 2017, rhodium traded at roughly $25 per gram. Over the next year, it climbed nearly $22,000 per ounce, making it at its peak approximately 12 times the price of gold. That kind of a movement is not normal even in the metal market. Today it sits around $200 to $400 per gram, still far above most metals. Rhodiums also show up in something personal. That bright white finish on the white gold and platinum jewelry is almost always a thin layer of rhodium. We always explain it to our clients that visually you're not going to see the difference between the white gold and the platinum ring. You're looking at the rhodium. It's what gives it a white gold, that mirror-like appearance. Most people who own white gold ring are wearing rhodium every day without even knowing it. So this metal exists in two worlds at once: industrial system and personal object. Osmium. Osmium was discovered in 1803 and named after Greek word of smell because of the strong odor of one of its components. But what defines osmium is not its name, its density. At about 22.6 grams per cubic centimeter, osmium is the densest natural occurring element there is, roughly twice as dense as the lead. Take a small piece and it feels heavier than almost anything the same size. That kind of the density sounds useful. In practice, it isn't. Osmium is hard, brittle, and difficult to shape. Early light bulbs manufacturers usually used osmium wire as filaments before tungsters became the standard, but osmium was too rare and too difficult to work with. Some of its compounds are also heavily toxic, which limits where it can be used. So instead of everyday application, osmium stays in a specialized environment. Fountain pen tips, pacemakers electrodes, scientific instruments, controlled condition. It trades in the wide range, roughly $400 to $1,000 per gram, depending on the form and availability. So unlike gold and platinum, its value doesn't come from widespread use. It comes from being extreme in a way that's difficult to apply. Protactinium. Protactinium sits in a completely different category. It's a radioactive element discovered in the early 20th century. Its name reflects its position in the decay chain. It appears right before actinium. It doesn't have practical everyday use. It exists mostly in research. What defines protactinium is not demand, it's extraction. This element appears in extremely small quantities, and it's very difficult to isolate from surrounding metals. In one historical example, about 125 grams of protactinium were extracted from around 60 tons of nuclear material. 60 tons of ore yield less than the weight of the baseball. That's actually quite extreme. It tells you what you're actually paying for, not for the metal itself, but for the effort required to separate it. Its estimated value falls somewhere between $10,000 and $50,000 per gram. At this point in this list, price stops reflecting usefulness. It reflects difficulty of extraction. Californium 252. Californium marks another shift. It's not mineral, it does not exist in usable quantities in nature. It's created. First produced in 1950s in the University of California, Berkeley, californium is generated through nuclear reaction inside reactors. And the scale is extremely small. Global production is roughly 30 to 40 micrograms per year, not grams, micrograms. But what it does with that amount is what matters. Californium-252 is the neutron source. The source in the size of your little finger can emit up to 100 billions of neutrons per second. That level of output allows it to be useful in highly specific environments, analyzing underground formation in oil exploration, scanning aircraft components for crack and trap moisture, detecting explosive and landmines, starting nuclear reactors, and certain cancer treatment. All of that from an amount so small that almost invisible. The value is not based on quantity, it's based on capability. The estimate cost is around $20 to $30 million per gram. At this level, the idea of buying or selling becomes abstract. You are not trading material, you fund in the production itself. Astatine. Astatine takes the idea of rarity further. It was discovered in 1940 and its name comes from the Greek word astatos, meaning unstable. That definition is quite accurate. At any given moment, there is an estimate to be less than 1 gram of astatine present in the entire Earth crust. It forms as a part of radioactive decay and then disappears just as quick. It doesn't accumulate, it doesn't persist. To study it, scientists have to recreate it artificially in extremely small amount, and even then it exists only briefly. Despite that, it has potential. Certain isotopes of astatine are being studied for targeted cancer therapy where radiation can be delivered precisely to the specific cells. So even at this level, there is a still connection to the real world application. It estimates value at around $100 million per gram, but the number is theoretical because in practice it cannot be stored, traded, or used in bulks. At this point, instability becomes more important than rarity. And finally, francium. Francium is the most extreme example on this list. It was discovered in 1939 by Margaret Perey and is the last element to be found in nature. And it's also most unstable. At any moment, there are about 20 to 30 grams of francium present on Earth, constantly being formed and destroyed through the radioactive decays. Its most stable isotope has the half-life of about 22 minutes. That means if you couldn't collect it, half of it would disappear before you had time to do anything with it. So in practical terms, it cannot exist as a sustainable material. It cannot be stored, it cannot be accumulated, it cannot be applied. It has never been weighted. Its physical properties, color, density, melting points are calculated from theory, not measurement. It has no industrial use, and yet if you try to assign its value, estimates reach up to $1 billion per gram, which makes it the most expensive metal on Earth at the moment, and also the least accessible. At the bottom of this list, metals support real systems, engines, electronics, infrastructure. In the middle, they represent the value, material people recognize and trust. And at the bottom, something changed. Those elements are so rare, so unstable, so difficult to produce that they almost stop behaving like materials at all. At that point, price no longer reflects what something does. It reflects where it can exist long enough to matter. If you like this video, let me know in the comments because I want to do more of those videos that not quite related to the jewelry topic but are broadly interested. Give me your feedback, it truly matters for me. Thank you so much for watching.